Okay, so first of all, thank you for the opportunity to come and talk to you all here today about the project, the UK BiLEVE project. I'll give you a little bit of an overview about the traits that we're interested in, which is specifically chronic obstructive pulmonary disease and lung function. Tell you what genome-wide association studies of lung function have told us to date, and then move on to talking about the UK BiLEVE project. So COPD, it's a major public health concern. The biggest risk factor for COPD is, of course, smoking, but it does have a genetic component. Diagnosis of COPD is in part based on lung function, and the particular lung function measurements that it's based on I'm going to be talking about are FEV1, which is the total amount that you can breathe out in 1 second, FVC, which is the total amount that you can breathe out overall, and then the ratio of those two measures. So over here on the right, we have someone having their spirometry measured, and here we have a volume time curve, and in black you can see what you'd expect to see in a healthy individual, and in red what you'd expect to see in somebody with obstructive airflow. Because lung function measures are used in the diagnosis of COPD and also for grading COPD severity, we can hypothesize that identifying the genetic determinants of lung function can also tell us something about risk of developing COPD. With that in mind, there have been some large meta-analysis of GWAS of lung function to date, and so beginning with two large consortia which published at the same time back in 2010, identified 10 loci associated with lung function and confirmed a previously reported loci. Spirometer and Charge then joined forces, brought in some additional studies, undertake another meta-analysis, and identified an additional 6 loci associated with either FEV1 and or the ratio of FEV1 over FVC. Also, earlier this year, published a meta-analysis which identified a further 6 loci which showed strongest association with FVC. These studies were meta-analyses of GWAS based on HapMap imputation of 2.5 million SNPs. And I've shown in bold those loci which have since gone on to show association with COPD in a case control setting. So the 26 associations with FEV1 and the ratio have identified proteins and pathways which hadn't previously been reported in lung health and disease. Interestingly, none of those reported were driven by tobacco addiction, and none of them showed any evidence of a smoking interaction. We believe that most of them probably affect lung development, and this is because we see a really high correlation with the effect estimate sizes and direction between adults and children. However, collectively, they still only explain a really small proportion of the additive polygenic variance, so for example, 3.2% for the ratio. So just to summarise, these large GWAS and meta-analyses of GWASs have largely focused on common variants, so that's variants with a minor allele frequency greater than 5%. They've collectively identified a number of loci associated with FEV1 ratio or FVC. There are functional studies ongoing to follow up some of these loci to identify why they're showing association with lung function. But there's still quite a lot of unexplained variants. So there's various potential explanations for this. For example, structural variation, so copy number variation where genes or select parts of genes are duplicated or deleted. Epigenetics. It's also possible that there are additional common variants which haven't yet been detected, which will explain a little bit more of that variance. However, low-frequency variants and rare variants have been so far underexplored with relation to lung function and lung health and disease. When I say low frequency, I'm referring to variants with a minor allele frequency between 1% and 5%, and when I say rare, I'm referring to variants with a minor allele frequency less than 1%. So with this in mind, the UK BiLEVE consortium was formed, and this is led by Martin Tobin from the University of Leicester, Ian Hall from the University of Nottingham, David Strachan from St George's in London, and me. And the idea of this was to sample individuals from the extremes and middle of the lung function distribution from a really, really large biobank, and I'll come on to that biobank in a moment. And to use a custom genotype array design to identify novel associations with lung function and smoking, and to give additional insight into previously reported loci and the genetic architecture of lung health. So the very large biobank that we sampled from was UK Biobank. So UK Biobank contains just over 500,000 participants who were sampled between the ages of 40 and 69. They have extensive questionnaire data and physical measures, including spirometry and a source of DNA. I'd encourage you to visit the UK Biobank website for more information about what specific information is available on those individuals. Self-reported ancestry, about 473,000 of European ancestry. And within that, about 430,000 had more than 2 measures of FEV1 and FVC, so this is important for repeatability. When we were choosing our sampling frame for UK BiLEVE, we wanted to focus on those individuals that had really high quality spirometry, so we selected from individuals who had spirometry measures which met strict European and American quality criteria. And this gave us a sampling frame of about 276,000 individuals. We sampled 50,000 individuals. We sampled these based on percent predicted FEV1, which is FEV1 after taking into account age, sex, and height. We selected from amongst the never smokers and from amongst the heavy smokers, and we selected individuals from the low, average, and high portions of the percent predicted FEV1 distribution. Just to add that if we look within our heavy smokers at the low end of the percent predicted FEV1 distribution, we see around 5,000 individuals who, based on spirometry alone, would have COPD which met gold stage 2 and above, so that's a measure of severity of COPD, so these would be moderate to extreme COPD. This shows the mean percent predicted FEV1 in our 3 groups by age. So here at the top we have the high FEV1, average and low FEV1, and the solid lines are the never smokers and the dashed lines are the heavy smokers, and you can see we get good separation there, so we truly have got the extremes in the middle. So moving on to the array design, I'm going to focus on 3 particular components of our array design. There were other categories of markers included to facilitate discovery and further insight into a broad range of other phenotypes. I'm just going to focus on the 3 that are most relevant to our project. Again, I'd encourage you to visit UK Biobank and also Affymetrix for more details on the array. And a version of this array, which is highly similar, is now being used to genotype the remaining 450,000 individuals in UK Biobank. So the array consists for us of 3 main components. So the exome chip style content. So many of you will be familiar with the existing Illumina exome chip and Affymetrix exome chip products. We use data from the UK Exome Chip Consortium and other sources to identify variants which we would expect to be polymorphic in the UK population. We also included some data from other sources, specifically exact European exomes. As I said before, the minor allele frequency, low minor allele frequency variants have been underexplored in relation to lung function. So we wanted to really try and explore this area. So the imputation grid that was included on the array was designed specifically to improve the imputation in this range, and this was done by a series of booster panels to, first of all, optimize imputation in Europeans in the common range, and then also to optimize imputation in the low frequency range. We also included a number of SNPs which were included specifically for discovery of and further exploration of known lung function loci. So we optimized the coverage of regions which had already shown genome-wide significant evidence of association with lung health and disease. And we also included variants which had shown suggestive evidence of association with lung health and disease in previous GWAS. So these had shown p-values of less than 10 to the minus 4, but hadn't shown significant association either genome-wide or at a level that we would have taken forward for follow-up. We wanted to achieve really good imputation coverage of the regions that we'd previously identified as being associated with lung function. So here at the bottom is a chart that shows imputation quality here, and now 26 regions, and we wanted to achieve an imputation quality of at least 0.8 or above. Here, and you can see that for nearly all of the regions we achieved or exceeded that target. One exception being the MFAP2 region, but we do know that that region is quite complex with a lot of structural variation, repeat sequences, so it wasn't really a surprise that that region was a bit harder to really cover. This was data provided to us by Affymetrix at the design stage, which showed the proportion of variants in the common range and the low frequency range, which achieved a minimum imputation quality of 0.8. And we'd expect to see an improvement on these numbers when using larger reference panels for imputation. So this is just a walkthrough of the pipeline. So this was the first genetic study in UK Biobank, so none of the DNA had yet been extracted at this point. We received all of the phenotype data for the 500,000 from UK Biobank, selected samples based on the criteria I just talked about. We then randomized these samples and provided this randomized sample list to UK Biobank. They then undertook the DNA extraction for those samples and then shipped them to Affymetrix in California for genotyping. The genotyping was undertaken in 11 batches of about 50 plates each, and the genotype calling was also undertaken in these batches. Variants which had a minor allele count of less than 6 in any batch were also recalled for that batch using single plate recalling, and this was based on some further investigative work undertaken by Affymetrix. And then the genotypes were provided to us at Leicester. We used clustering QC provided by Affymetrix, and we did some further QC, and we also undertook imputation and association testing in-house. So this is an overview of our sample QC. So we started off with with 50,500 because we included an additional 500 duplicate samples so that we could assess reproducibility of the array. Samples were filtered based on DNA quality, call rates, sex mismatching, heterozygosity, and duplications, and I'm just going to focus in on a couple of those metrics. So first of all, sex mismatch. So this slide shows the X heterozygosity rate on the y-axis against the XY ratio on the x-axis, and as expected, females have a high X heterozygosity rate and a low XY ratio, and males have a high XY ratio and a low X heterozygosity rate. We identified a small number of individuals who had an X heterozygosity rate indicative of being female, but an XY ratio indicative of being male. And when we looked at the expected prevalence of XXY in our population, we found that the numbers that we were seeing were consistent with that, and we provided this information back to UK Biobank. The other point I'm just going to focus on is PCA. So if you recall, the ancestry that we based selection on was self-reported, so we wanted to confirm this, so we undertook principal components analysis. So this plot just shows principal components 1 and 2 for the HapMap3 population. So we have the East Asians up here, the Europeans here, South Asians and Africans. And if we superimpose the UK BiLEVE samples in black over the top, you can see that the self-reported ancestry was pretty accurate for most of them. A very small number lay outside the 10 standard deviations from the mean. We excluded individuals outside of these thresholds, and we also included the first 10 principal components in our analyses. So we included about 500 spike duplicate pairs so that we could assess reproducibility across plates and batches, and we had really high levels of reproducibility, so that was really good. Affymetrix also included 1,000 genomes project control samples on each plate and checked concordance, and again that was really high, so these are further confirmation for us of the quality of the data. SNP QC, so we used the standard SNP clustering QC metrics which were provided by Affymetrix for clustering, and we also did some additional checks of plate and batch effects because our samples were extracted and shipped in a series of batches over a number of weeks and months. So this is the approach that we used to check for plate effects, and we used pretty much the same approach for batch effects. So we took high quality probes and samples, and for each probe in each batch, we created a contingency table of allele count for each plate, and then just simply performed a chi-squared test to see if allele count was dependent on plate. This plot shows the number of variants which failed either cluster QC, plate effects, or batch effects in N batches. So on this axis, we have the number of variants, and on here we have the number of batches in which the SNP failed filter. So for example, just under 50,000 SNPs failed cluster QC in only one batch, and a very small number failed batch or plate QC in one batch. Because we didn't want to throw out data, we wanted to keep as much data in as we could, but at the same time we didn't want to include bad SNPs in the analyses. We made the decision to keep all SNPs which passed QC in 9 or more batches, and in those batches in those 1 or 2 batches where they failed, they were coded as missing. Because we were undertaking imputation for many of those SNPs, we would be able to rescue those genotypes at a later stage. So we ended up keeping about 97% of our SNPs after QC. The imputation panel that we used was a combined panel. We used the 1,000 genomes phase 1 combined with the UK 10K panel. So the UK 10K is about 3,600 individuals from the Twins UK and ALSPAC cohorts in the UK who had whole genome sequencing. And this plot here just shows the imputation quality as measured by info and impute against minor allele frequency on on a log scale, and comparing the quality when you're using just the 1,000 genomes panel alone compared to using the combined UK 10K plus 1,000 genomes panel. And you can see that particularly for the variants with the minor allele frequency between 1 to 5 and less than 1%, that there's a real improvement in the quality of the imputation when using the combined panel. After excluding variants which had a minor allele count of less than 3 and those which had an imputation info of less than 0.5, we had about 28.5 million variants which we could then take forward for association testing. Just a reminder of the nested case control comparisons that we were undertaking. So we were comparing low versus high FEV1, low versus average FEV1, and high versus average FEV1. And we were doing this separately in heavy smokers and never smokers. And we were also looking for variants associated with smoking behaviour by comparing heavy smokers and never smokers. And just a point to add here that because we had 10,000 low and average FEV1 and 5,000 high FEV1, for variants with the minor allele count of less than 400, which was showing significant association using a score test, we also repeated those association tests, used the first test to make sure that this wasn't a consequence, an artifact of the statistical test. So just a very quick overview of our findings, and if you want more details, please come and see me at my poster. For the extremes of FEV1, we confirmed many of the previously reported signals, and we identified some new loci. Amongst the new loci that we identified, some of them did show evidence of interaction with smoking, and there are common and rare signals in there. Similarly, for smoking behaviour, we confirmed previously reported signals, and we identified some novel signals. For us, the key benefits of the array design were that many of the novel signals, particularly the common signals, were actually directly genotyped on the array, so it wasn't depending on imputation to find them. And also, because we'd included extra custom content in some of our previous reported regions, this was able to give us additional insight into those regions. So just in summary, UK BiLEVE, we've identified novel loci for lung function and smoking and additional insights into known regions. We will be making our GWAS results publicly available. As I said before, the UK BiLEVE array is highly similar to the array that's now being used to genotype the remaining 450,000 UK Biobank samples. We're really pleased with the quality of the genotype data and also with the performance for imputation. And the genotypes of 50,000 individuals have been deposited back with UK Biobank to be made available with the rest of the UK Biobank genotypes. So finally, I just want to thank everybody, so the other UK BiLEVE investigators, steering group and analysis group, the team at Leicester, particularly Nick, who did a lot of the really heavy analysis. Thanks to the chip design group, and really importantly, the participants in UK Biobank, and a massive thanks to the MRC for funding this. Thank you.